So welcome to week 10 live discussion session of quantum chemistry of atom and molecule. So today we will discuss mainly some concept related to the time independent perturbation theory, and then we will directly go to solve the assignment 7 problem, and then we will try to solve some more numerical problems. But before solving all those problems, I will just build the concept for the time independent perturbation theory in non-degenerate systems, or line by line, so that uh, it would fall so that we can solve with the appropriate what are the formulas, what are the questions that sometimes comes in CSI and NET. So we'll try to follow that pattern. So that we will start with the derivation of the first order and second order correction, and let us start then. I already given you the outline what we are going to do, so I will just write it down once. So we'll start with the time independent perturbation theory for non sorry for that. So non-degenerate means we are going to discuss for those systems which have no means different energy levels. So these states like psi 0, psi 1, or these kind of states have different energy. If they are having similar energy, then they are degenerate state. For their the expressions are little different, which was already discussed in the lecture by Professor Datta, I guess. But that is actually a little bit difficult also to follow, and the questions will mostly come from this non-degenerate part, but we should also check those formula or expressions, so that if some numericals are coming, we are able to solve that. So we'll for now we'll only discuss these non-degenerate systems. So in the normal, when there is no perturbation, then how we write the Schrodinger equation? So I will write it once. Schrodinger equation for a un for an unperturbed system can be written as Hamiltonian at zeroth order. So I guess you have already understood this. We are not calling it H0. This is zeroth order. So psi n zeroth order V equals to energy of the nth state, zeroth order means there are no perturbation. So this is an eigenvalue equation as we are writing it for the whole course till now. Now suppose are very small. So the cases we are right now we are going to discuss, these are very small perturbation. So 1% or even 0.1% of the actual system. So that means there is no change in the other part of the system. Wherever we are applying the perturbation, this part is only getting perturbed, not the whole thing. So the change is going to be the perturbation is very small. So if we have to write the perturbed Hamiltonian, suppose there is a perturbation is applied. So perturbed Hamiltonian and and let me write it a function of lambda. I hope you remember what lambda is. I will write it. So obviously it will have the zeroth order perturbation plus this part of the Hamiltonian, this perturbation. This is the perturbation. Okay. I know what Professor Datta has done in the class, a little different approach from this. So please try to follow, and if I am making any mistake, please let me know. So this lambda is going to be very, very small, and due to that this perturbation, this is going to be very small perturbation. Okay, and due to that obviously there would be some correction to the wave function and the energy as well as. So the modified wave functions will look like something like psi n. Obviously again it would be a function of lambda. Let us write it like that, psi n zeroth plus, now I'll write the correction terms. So this is after the perturbation, effect of perturbation. Lambda square psi n 2 and so on. In energy, how we will write the energy? Energy we will write it then lambda to the power 2 lambda square. Oh, I made a mistake, sorry. This should be En, right? Then En second order, so on. So what are these two? So we already know these are unperturbed part. So what are these two? What are these two? So this is the first order correction to the first order correction. The above one is the first order correction to the wave function, and below one is the first order correction to the energy. So I'll just write as a common term first order correction. And what about this? The whole thing. So this is about second order correction. So there are obviously there are multiple order of correction can be there, right? So but as lambda increases, as you already know, lambda is very, very small. Now lambda square is going to be even smaller than lambda, and if you have to think about the third order correction and the fourth order, so that is going to be even smaller than this. So we will only discussing about this first order and second order correction for this course. So the higher energy, higher order correction are going to be even smaller than that. So the so this was the unperturbed system, the Schrodinger equation. Now how the Schrodinger equation for these perturbed wave function will look like? The Schrodinger equation and for the modified, let us write modified, or not modified, but the perturbed system is going to be, obviously now we will use the Hamiltonian, that is perturbed Hamiltonian, right, is going to work on this high n lambda and going to give us this energy. So this is going to be the Schrodinger equation for the perturbed part. Now what we will do, we will put individual values there. Okay, so this is, so I will go to the next page maybe. So this is going to be okay, record. So I'll go to the presentation mode and we will do it one by one. So obviously now what we will do is we will put the values there, right? Here is my, I just write it the Schrodinger equation once more so that it could be in the same page. Okay, now so what was my modified the part of Hamiltonian? That was the original one, zeroth order, and the part was there, right, multiplied by my modified wave function, and this will go on, and the right hand side it is lambda en 1, not 1 en 1 first order, en second order, and it will go on, and obviously there is the your this is there. Now you can understand that we need to expand this equation, right, for the LHS and RHS both. And what we will do, we will expand it such a way that we'll take everything to the left hand side and keep the right hand side as 0, and we will try to collect the term which has which are in the same order of lambda. So in small or in short, I will say, so we are going to collect the term with respect to lambda to the power 0, that is nothing but 1, right, means the lambda independent parts. Now next we are going to collect the parts where your lambda to the power 1, that is lambda, is common. Now we are going to collect the terms which have lambda square as common, and that will obviously go on, and right hand, as we have taken all the things to the left hand side, so the right hand side will be 0. So let us collect the terms, and here I will give you, I will tell you a trick how to first let us do that, and then I will tell you the trick. Obviously I have to multiply this with this, so H naught or H first order, I am taking first order, psi n 0th order, and see that is only going to be the thing that has lambda independency, and in from this part only en 0th order and psi n 0th order are going to be the only thing which doesn't have lambda. So this is the first thing. Now what about the equation related to the part related to the lambda which have lambda as a common thing? So obviously you will see when we multiply h0 with lambda psi n1, so that not h0 but 0th order, we sometimes while we speak the wrong thing, and then also this These multiply by the first part that also have lambda common. So now if we are going to have something else that is going to have lambda square or higher order of lambda, so this LHS is done for this case. Now we have to look at the right hand side and take these things into the left hand side, so that we'll have minus to start with, and similarly we have En 0th order, psi n first order, then we will have En first order, psi n 0th order. So this part is also complete. What about the part related to the lambda square? So I know we are going to have a little far more parts here, so I will first write it. So obviously we will start with 0th order Hamiltonian and psi n second order. What about else? We will have something like this lambda h first order multiplied by lambda psi n first order. Both of them are going to have, then they will have lambda square. What else? Nothing from this side. We have to look at to the right hand side. So En naught or En 0th order with psi n second order, then we have En first order with psi n first order, we will have En second order with psi n 0th order, right? And not more than that, and that will have, so I'll try to write this part here, then I'll erase that so that we I'm just writing this thing here so that we have some space on the right hand side. And then obviously we are not interested about the other terms in lambdas, and obviously this part is going to be 0. And before that, let me erase this, right, because we have already written it down on the below. See, from here we can say that when, so in lambda's parameter, whatever common is there, so if we can write it in a same fashion and we can equate it to 0, then this individual things are also going to be 0. Then only we can equate it to 0. So this is, we can write 3 terms from here. I will write it in different color, that you n should be 0, so that this can be equated to 0. What else? Should be equated to 0. Oh, I told you that I will write it in a different color, right? And what else we have another equation here that is related to the lambda square, right? This have to be equated to 0. Now see, then only we can say that this overall equation is going to be 0. These are the conditions, and what individual information we can get. So this is nothing but the Schrodinger equation for the unperturbed part, right? The unperturbed part. But when you check the second equation now, the second equation tells us about the first order correction, right? So we will get information of first order correction from this equation. What about the third one? Obviously we will get information of second order corrections. Okay. Now before going to the before going further, let me give you the trick I was talking about. Not trick, but to validate if you have written all the terms properly. See, here we are discussing about the lambda to the power 0 term. So you can see that all the order, if you add them up, that would be 0 for that, huh? When you are looking at lambda to the power 0, which is 1. So 0 0 0 0. Okay, now you'll understand. We are looking for the terms related to the lambda to the power 1. Now see the order: 0 plus 1, 1 plus 0, 0 plus 1, 1 plus 0. There are nothing like 0 0 or 0 2 or 1 1. So the addition of the order will lead to the lambda to the power the 1. So that terms are going to be there, not more than that. Now see, for lambda to the power 2, what are the order we can expect? 0 2 2 0 or 1 1. See, the terms only they have in the order. See, 0 2 1 1, 0 2 1 1 2 0. So by that way you can cross check that you have all the terms or not, you have written all the terms or not. Okay, now I hope this was useful. So let us now work with the we will first work with only the first order correction. We will see how can we get the first order correction to the energy and all. For that we need to work with the second equation, right? So I'll write it here one by one. This is second, this is third, this is first we have worked so far. Now we will work with the second one. I'll just write it here once more. I will not try to look at the previous thing. So if this is 0, then this is going to be 1. Now if this can be 1, this order would be 0. Then the same way okay, here 0. So we are going to see that what is the value of first order correction to the energy, huh? So what we will do, we will start with, let us lift multiply the equation with psi n zeroth and complex conjugate of that, and integrate all over the space. What we will get? So we will get first term as d tau. Obviously we are integrating. The left multiply we are doing psi n star zeroth. We have this unperturbed Hamiltonian psi n1. This is the first term. What is the second term going to be? Integral d tau, obviously psi n star zeroth. Now first order Hamiltonian perturbation. Now psi n zeroth. Okay. What else we have? Now we have a, these are constants, so we'll keep it outside the integral d tau psi n zeroth star of that and psi n 1th first. And what else we have? En first order psi n zeroth complex conjugate of that, obviously left multiplying d tau and psi n zeroth. Obviously if we multiply anything this side, doesn't matter, it will become 0. Now see, this psi n zeroth order is already a normalized wave function, right? So see, this integral d tau psi n star psi n zeroth complex conjugate of that multiplied with psi n zeroth order, this is a normalized case from this part, only the integral, so that would lead to 1, right? That is a normalizable condition. And what else we have? We know that all the operators are Hermitian, or quantum mechanical operator are going to be Hermitian, right? So this operator, the Hamiltonian, is also Hermitian. If it is Hermitian, it has some certain property. So the mathematical definition of psi is not, so if it is Hermitian, we can write this term, the first term, psi n star zeroth this we can, as this is a Hermitian operator, we can do this, that we can take a whole square, we can take a parenthesis, obviously I will d tau and psi n star of this first order, then we can write our Hamiltonian and write our zeroth order and take a complex conjugate of the whole integral, and this will lead to, obviously when each first order is going to operate only on the psi n zeroth, not on the psi n first, right? So that way we can see there is an what we are going to get, we are going to get en zeroth, right? When this operator operates on psi n 0, it cannot operate on psi n 1 first. So now this is going to give me d tau psi n star first order, obviously psi n zeroth order, and we have got the eigenvalue outside of the integral because it is constant, and we should not forget the complex conjugate of the whole thing. Now as these are Hermitian and this is an eigenvalue, you already know this is going to be a real thing, so star complex conjugate of the real thing is going to be same as that, and this part integral is going to be d tau. Now complex conjugate of psi n star first order is going to be, is, I will write this thing first, psi n star 0, then this is going to be complex conjugate of this. So we are going, we can see the first term changes to zeroth order d tau psi n star 0 and psi n 1. Okay, fast. Now second term will be same as previous, and this third term also same as previous. But now see, if first term and this part are equal but have opposite signs. Okay, and these are en 1, huh? Because this part is one normalized condition and equals to 0. What I was talking to you is that see, the first and the third term are equal and opposite sides, so they will cancel each other and leads to, I'll take en to the other side of the equation and lead to d tau psi n star 0th, your perturbation n 0. Or this thing we can also write in terms of bracket notation, n 0th, your perturbation. Okay, so now what we can see that the first order correction to the energy is going to be what? This En1. Not only this, but you should not forget lambda. Sometime in the questions, lambda can be given in such a way. In perturbation term, you can see the lambda. So that time you don't have to use lambda outside. But if it is nothing is given, better to write it like that. Lambda psi n 0th and this is the, and you can also say that lambda can be very small than 1. So this is what gives you first order correction to the energy. So this is the first order correction to the energy. Now what about the first order correction to the wave function? So for that we will write the same equation, but we are going to left multiply with a different wave function, not complex conjugate of a wave function, not with the psi n 0. I will show you why. So what I was saying that, let us write the wave function again. So now what we are going to do, we are going to write the wave function once more. This is the main equation what we are writing. Now we wanted to know what is psi n first order. So before doing that, as you know, this unperturbed wave function, that psi n 0th order or psi m 0th order, they actually form a complete set. What do I mean by a complete set? Means in this uh, uh, in that, so these wave functions or these states actually we can take a linear combination of those unperturbed wave function and can write any wave function in we can take any linear combination to write any these things. So let me write it down what I am trying to say. The so in that space, as they are making a complete set, we can write any wave function. So we, for now we will, as we want to know psi n first order, so we will write that. We can write psi n first order as a linear combination of unperturbed wave function. How? That is here sum of m can be starting from 0 to lambda infinity Cm coefficient of this and psi m, obviously unperturbed wave function, so 0. But you need to also write the, as we are writing this for the nth wave function of the first order correction, we are looking at the first order correction to the nth wave function, so we need to mention it here also, Cm nth. Okay. So this is not the order but identifier to the as we are working to the nth wave function. Okay. Now what we can write, we can write the, obviously these things psi n1, we can change this wave function. Let us do that. So how it will change? Will h not m equals to 0 to infinity Cm n psi m 0th, there won't be any change. There is going to be a change. Okay. Now earlier we have what we have done, we have left multiply the equation with psi n 0 and complex conjugate of psi n 0th. But here we don't want to do that. We want to multiply with psi a complex conjugate of psi l 0th, another 0th order wave function. Okay. And what do I mean by left multiply? Left multiply means I am multiplying from the left hand side. We are not writing the psi l this side. We are writing the psi l on the left side of that and integrate all over this bit. What we are going to get? Obviously, we will write the summation this side infinity. Then we have this, and and then we have d tau as we are integrating all over the space, and as we have left multiply psi l zeroth, we have the zeroth order perturbation and we have m zeroth. As we have not multiplied with psi n zeroth, so we will have some conditions to play with. If we had a multiply with psi n zeroth, then again we would have gone to the same thing, the correction to the energy term. I will show you how why did we take L here, not N. I will show you. I'll just wait a few time for a few minutes. Now this is the part of the function psi 0. Now here again m equals to 0 to infinity cm n en 0 d tau psi l star 0. This is the factor we have left multiplied with, and this is what was there earlier. And okay, I will try to keep I know there are many things are there, but please try to focus what I am saying and what I am writing. And if you can write it by yourself, then you will get the gist. You can have the better idea also. Not n but l. It's talking, and obviously it had psi n 0, and obviously that all equals to 0. Okay. Now see, there is a summation terms are there, right? And m can vary from 0 to infinity. M can be any number, any integer, any positive integer, 1, 2, 0, 1, 2, 3, 4, anything. Huh? Now m can also be n or m can also be l. Means as all of them m, n, these are all positive integers, right? So the value of n can m for so this m I am talking about, mango. So that can be anything. So see, for all the values of m here, what are we looking at? When h naught actually, so let me write another line maybe. So I know this doesn't add much, but as you can see, I will not try to do the step jump. See, h first order, Hamiltonian first order is a so this is a so psi m first order is going to be a eigenfunction of this operator Hamiltonian, unperturbed Hamiltonian. So obviously it is going to give me that energy value or eigenvalue, that I will write it outside. Okay, and actually rest of the part is same. So our main goal would be to simplify this equation by erasing or deleting as many terms we can, and for that we need certain conditions, and I will show for which condition we are going to get what. So the main target from this
exercise is going to get some form of this coefficient, some expression for this coefficient, so that we can get the psi n first order term, right? We are looking for what we are looking for. We are looking for the correction term to the wave function. So for that we need to get some expression of this. So for that we get this whole this lengthy equation which looks very dangerous and very big. So what we will try to do, we will try to omit some of the terms by taking a few conditions. And what I was saying that the m, l, n, these are all positive integers, so we need to play with the values of m and l, and for that we have some summation values, right? Summation means the m can be from 0 to infinity, anything. It can be l, it can be n. So suppose the condition for which m is l, so that time you see this part of the wave function, this here once here, huh? See these two part, there are summation involved. See, only when m equals to l, this is a normalizable condition, right? Else we know these wave functions are orthogonal, so they are, or sorry, they are orthonormal. So when m equals to l, it is a normalized condition. When m not equals to l, that is a orthogonal condition. For orthogonal condition, that integral is going to be 0, and whenever m is going to l, only for m equals to l value, only for that condition, this is going to give you 1, and rest of the case it will be 0. So summation of all these terms will lead to only one value will survive. And summation means there are multiple terms, right? For m equals to 0, 1, 2, 3, anything, but all the term will vanish, only m equals to l, that part is going to survive. So now I can remove the summation, right? Because all the terms are vanished, only m equals to l is there. So I'll replace all the m with l, and this will be a normalized condition, so I'm not writing that. Should I write? Let me write once at least. Okay. What about this? This will be unchanged. Psi l star 0th. And now this summation is also going to vanish, because most of all but m equals to l terms are going to survive. So that is Cn. So I have made a mistake here. I should have written L, because I have only these terms are valid, and obviously this is also will remain as it is. So for this step, by taking m equals to l, and means not taking m equals to l, this term is going to survive, and all the terms, other terms are vanished. So we have shortened the equation, right? There are multiple terms involved. Now we have shortened the equation by thinking intelligently, right? Because all the other terms are going to vanish. They are not going to be they are not going to influence or take part into the thing, right? Only this is going to survive. So let us also write that now this is going to be 1. Why? That is why this part has survived, else it would have been 0, this integral. I hope you are following my what I am trying to say. So now next I'll write this part. If you remember, we have two terms where the CL n is common here and here. So I will take a common of this. By taking a common, what we are going to get? 0 common. Here we will get EL 0th minus EN 0th. Okay. What else we have? We have this integral d tau psi L star 0th H1 first order perturbation. Those things I will write it down. And as we have taken this thing already, and this is, we will take it to the right hand side, so this minus will become positive, and still there are multiple terms are there, right? So we need to even short it down so that we can get something in terms of the CL naught, CL 0th. So see, now there are, what we have done, we have shortened it down to a condition where m equals to L, and this part has been survived. Now see, there are two integers kind of things are there, means two states, two kinds of state where kind of conditions where L can be equals to n or not equals to L. N means this thing, number, n for number, that n can be equals to L or not equals to L. See, in the previous case I told you, we are left multiplying with a wave function, 0th order wave function, where it is L, not n, what we have done for the, while getting the correct first order correction for the energy. See, if we would have taken n there, that means if L is n, then what we would have got, see, that's why I am writing it a different color. Obviously this is going to be 0, then all the L is n, so this is 0. See, now this is a normalized condition, this is also 1. We are getting back the correction in the energy, that term we are getting back, but we are not getting anything in terms of the coefficient, the CL, that is not there, so we are not going to get anything regarding the correction terms in the energy, the correction term in the wave function. So to get that, we need to take the condition. So we need to take the condition. So to take the condition where L not equals to L. So only that part is going to lead a non-zero value of this, non-zero value of this part. See, so now if we write it like that, that L cannot be equals to N, then I will write it again. Now see this part on the right hand side, this now has become the orthogonal condition. Why? Because n cannot be equals to L, so this is going to be 0. So what we have now? We have some form of CL which tells us this is d tau psi L star, H is the first order perturbation, psi n naught divided by EL naught first order. So we are getting something in this. So if I have to make it in a common term, that is so what was my ultimate goal? I want to get this psi n1. What is that? So should I write in a different color? May not be. Let me write it here then. So I want to get psi n first order. So that is what? That is some, I have taken it to be m equals to 0 to infinity Cm psi m 0th. Now I have the expression for this. So sorry, I have made a mistake here, maybe CLN. From here onwards I am making the mistake. Very sorry for that sloppy work. So what is this? This Cm n can be written like d tau psi m star, right? Instead of L, because what I have done, I have taken a condition where m equals to L, so I can also write a instead of L, I can write m, right? Okay. What is my psi n then? Psi n first order correction is summation and we need to make sure that L is not equals to N. What would happen if L equals to N? Then this part would have been blown up. See, right? So not only m equals to 0 to infinity, but also not equal m not equals to n. We need to make sure of that. And obviously in a bracket notation, let me write it for once. It would have looked like psi m star obviously 0th. Then your perturbation and your this divided by am0 minus an0th. Okay, what else was there? So this is only my Cm. this coefficient and I have to multiply with psi m 0. Okay, then only I am going to get my correction to the wave function, but we also have to make sure that there is this lambda is there, right? We should not forget this. If that is given inside the perturbation expression, then we don't have to think about that, but if it is not there, then we have to think. So now what? So this is my first order correction to the wave function. Okay, I hope doing it step by step you are also getting all the gist from it, that why we are doing this, why we have to take this kind of lengthier approach, and why these many mathematical terms are there, and what we are doing in each step. So we are trying, so for this, when why we take a different wave function to left multiply with to start with, and why, how we are reaching to each of these stages. I hope these things are clear. So in each step we are reducing the terms. So that is our main goal, how we can do that. There are multiple terms involved, right? So this is the correction to the first order correction to the wave function. Now we will go for the correction to the second order term, and second order term we will do the first as we have done for the energy, and then if time permits we will go to the wave function. If not, then we will go to the uh, we will go to the wave function or the assignment. Anyway, so now let me use a different color maybe, because we are now going to work on the third equation. If you, sorry for that. If I know you don't remember the third, so we don't have to remember this, right? I told you that we have a trick, so I will follow that, and nobody is going to ask you the derivative in any examination. I hope so. At least not in this NPTEL exam, because anyway you know you are going to have the MCQ or MSQ type of question. But this is not. If you do it step by step, then you don't have to mark up, right? And I also told you one interesting trick to remember it. I will just do it myself. I will not look at any notes or something like that. So this is 0 2, so this is one of the term. Now we are already working the lambda to the power 2 those part, right? Now obviously we have each one, then it will be 1. There are no such thing. Now if it is en2, let us start with en0, maybe en0th, then it would be psi in second order. Now if it is one order first order, then
last term, that is okay.
Now for the correction in energy, we'll only deal with the complex conjugate of the nth wave function, right? So let us do that. Let us left multiply the equation with psi n star zeroth and integrate all over the space. So first term would be integral d tau psi n star zeroth, right? Okay. What about the second term? Second term is going to be d tau psi n zeroth complex conjugate of that perturbation first order, then psi n, then d tau. Acha, I can write the en outside like this. So basically en zeroth, now d tau psi n zeroth. Similarly, I will write down the wave function outside. Basically, you can see now this is a normalized condition, and this will lead to 1, right? 1 for this part, en2 is going to be there. So, and also your this is a Hermitian, as we have discussed for the first order correction also, that as a0 is Hermitian, operator, this d tau. So we are just using the mathematical definition for a Hermitian. We can write it in d tau star 2, as we cannot operate this operator, the unperturbed Hamiltonian over psi n second order. We are using these things so that this psi n zeroth order comes this side, and we can operate with the Hamiltonian. So this is the only goal, to use the Hermitian property of this Hamiltonian. And complex conjugate of the whole integral. So this is the mathematical definition only. If H or this operator is Hamiltonian, then we can write this way. Obviously now this is going to work on that and going to give rise this d tau psi n complex conjugate second order psi n 0 complex conjugate of whole, and as this is real, this will come out of the thing d tau psi n star psi. Okay, it's going to be, just wait for a bit. Go to the Google Meet.
extension. Okay, let us come back here and we will put the value here that this is d tau. Obviously en 0 is there, d tau psi n star 0 to we'll write the other terms as it is for now. And obviously by doing this we are going to get some terms cancelled out like the previous part. See this third term again, this is going to be cancelled with the first term, right? So let us do it. This and this are cancelled because they have the same values, right? What else we had? We had n first order d tau psi n first order right, and this part is as we have normalized condition, so this is as it is, and this is equals to 0. So what do we have now? We have this Hamiltonian, the second order correction is equals to these two terms, that d tau psi n star of this right. Now if you remember, in the previous case what we have taken one not approximation, as this wave function in the zero unperturbed wave functions form the complete set, we could have write the psi n first order as a linear combination of all the unperturbed wave function in some linear combination, right? So let us take that you remember, right? We took this wave function, it took this approach that time, so we'll put the value of to there. So in the first case, okay, let me erase a bit. So this is m equals to 0 to infinity, now d tau is there, psi n star 0th first order perturbation, and then this 0th is there. Not much problem here, we have just here m equals to 0 to infinity, Cmn En first order. Now we have d tau psi n 0th psi m 0th. Okay.
If we take the condition that m equals to n, then what will happen? If, and also remember that I should write this to the next
Page and discuss again. Huh? Just wait, I will just rewrite this.
Okay, so this is what I have written, and also remember we have a expression for CMN, that is if I write it in terms of, as we are writing in integral form, let me write it in integral form only. Sorry, EM minus EN. Okay, so see, when m is, so m can be anything from 0 to infinity with this condition. Again we have a summation condition. We need to see that if all the terms are valid, or if all the sum of the terms are going to vanish and only one term is going to survive. So by that way, if you see here in the second term of the right hand side, that when m is going to n, then only that integral is going to survive. But if you check about the value of c of m or cm, that coefficient is going to, ooh, means bounce up, means that is, the value is going to be very large, because m, so because the denominator is going to be 0, so that is going to infinity, so that is not going to help us. So we need to take the condition where m cannot be equals to n. I hope you understand what I'm trying to say. So we have to take the condition where m is not equals to n. If m equals to n, then this integral would have survived, but the cmn is going to be very large, because that equates, then denominator is 0, then this is going to be very large quantity, that is not going to help. So we need to work with the condition where m cannot be equals to n, and that time this integral is going to vanish, so that term is going to vanish overall, right? So if we write
Now we have to write for all, right? Not equals to n infinity. I am writing this so that can just show once that as m not equals to n, this is 0, and because of that we are dealing with only the second part, first part, sorry. And if we write if we put the value of CFM from here, then we will get the summation m equals to 0 cannot be n infinity another integral d tau psi m star 0th. Acha, I have made a mistake, I guess. Go back to here. I guess I have made a mistake. That is nothing but, sorry for that. See, both the terms are on the same side, so if I have to take this on one side and this another side, I have to take this minus sign, right? And if I have to take this minus sign, then what I will do is just just write the minus for now. Okay, so if I have to do that, I have to write the minus here also, right? Can write the minus here in the numerator. If I have to remove the minus, then I can remove it by changing this n and m, right? And there is another integral which was there from the earlier. So their modulus is same, and so I will write it in terms of I will need a blank page maybe. State 30, so we need to solve the numericals too, right? So if I have to write it in terms of bracket notation now, then we have something m equals to 0 not equals to n to infinity, then we have from the first term, now this is the second,
The bracket terms always looks a little neater than
this previous case, the integral part, to me, to be specific. Someone can have affinity toward that. Oh, so as we are writing in bracket notation, we don't require the stars, right? The complex conjugate form, I hope not written it earlier. Okay, I have written it. So this is actually the wrong notation. Message will go. Okay, I can't be able to. So I'll just cut it. Huh? Obviously, in the denominator there is en naught, en 0th, en 0th, and we can short it down as modulus of see, the above term is a square, so modulus square, so that is always going to be positive, and the below term are the difference in energies of the nth and mth state of the first order, zeroth order. So depending on that, if you think of like that, for a ground state, for a ground state, n is always going to be lesser than m. So in that case, n0 is going to be less than em0, right? So n is something like 0, right, or 1, depending on the exactly solvable system. I am not writing m equals to, so by that way, let me not go into that part. If that is a ground state, if n is a ground state, right, so then you will see that its energy is going to be always going to be lesser than em0. So this part is negative denominator and the numerator is positive, as this is a square of something. So for ground state, okay, so I'm not finished yet, right? So I have, let me write it in terms of like, now the, if I had to write it in the correct factor, then I need to multiply the lambda square also. Oh, I'll just this is the second order correction to the energy. Okay, and lambda square is obviously less than 1, as lambda is less than 1, right? So as you can see, for a ground state, the first order, sorry, the second order correction to the energy is always negative, but keep in mind this is for a ground state, this is always negative, but for other states the statement is not always true. So that depends on which n you are looking at. If it is greater than m, obviously then it is a positive quantity. If it is lesser than m, then you are going to get a
negative value. And also you have to see this is a summation, right? This is going to be a summation. So obviously you have to look at the total sum. Anyway, for now what we can do is we can go to the assignment problems, as we have maybe 10 to 20 minutes left. So we can go to the assignment problems and solve them. So week 7 assignment solution. The first question says that, so please remember this last statement. This is actually very important for the CSIR net perspective. Actually, let me highlight both of them actually. So in CSIR NET or this kind of competitive exam, at least when I have given the exam, that time this kind of statement was very usual, that they have given a statement of multiple correct. It could be multiple, means something like not multiple correct questions, but if you what I remember, that this statement used to come, or some numerical used to come, which we need to calculate the yeah, the second order correction to the ground state, and all the terms are positive, and only some is only one is going to be the negative one. Now if you knew the this thing, that for ground state the second order correction is always going to be zero, is always going to be negative, then you could have choose the negative options only, right? You don't have to think about the you don't have to think about the uh, other terms which are positive. So you can remember that for ground state, the second order correction only for ground state, this statement is going to be true, that for the ground state the second order correction to the energy is always going to be negative. But for the other states, like for n equals to other than m, this could be either positive or negative, that depends on the summation or whatever the value you are getting. But for the ground state it is always going to be negative. Now let us go to solve the assignment problems. uh, the first question states, what is the turnover rule, that is integral of f star a g d tau, which is equals to the g a, the operator and complex conjugate of that, and f complex conjugate d tau, holds for the operator that are, obviously those are Hermitian, right? Not for other operators but for Hermitian operators. Now the expression for the first order correction to the energy from the perturbation theory is delta E, is obviously we have already solved it here, right? Here the first order correction to the, no, this is for the wave function, this is for the energy. As you can see, this high n zeroth order, inside the bracket notation, obviously the first order perturbation and psi n zeroth. So you can see the C option is going to be the correct option. Now question number 3, perturbation theory works for the system for which deviation from an exactly solvable Schrodinger equation is, as I told you before starting, that whatever in perturbation theory or approximate method, wherever we are using any approximation method to a exactly solvable system, we consider the perturbation to be very small. So here it is, if it is undefined then we can't work with this, if it is 0 then there is no perturbation, if it is large then we cannot use the perturbation theory for whatever we have solved yet or determine the expression. The perturbation has to be very small. Now question number 4. For question number 4, the image is already given this side, that for a particle in a box with x dependent potential as shown above, delta E is going to be what? See, the box is like this. Usually the first order in a 1D box, what we have shown, that this it's gone through this, and the potential inside the box is 0. Now what is given, that for a particle in a box there is a x dependent potential. There is a potential. So if you look at what is the perturbation expression for the perturbation, if you think like that, then there is a linear correlation, right? The potential is increasing linearly. So it is a function of x, obviously the potential, and we can write it that v of x is equals to, we need to write it in some expression. So we will write it like x by a multiple by v. Okay, v is the potential given. See, v is the potential at a, vx. So v of x. So why, how? So what is the means? How can one can argue that how did you get this value? This is not given. So this is the expression for this potential we are obtaining from this picture. Whatever is given, that it is linearly increasing, right? X dependent potential. See, at x equals to 0, here what is going to be the potential is, from image you can say there is no potential, right, at this point. So see, put the value of 0 at x, so 0 by a into v, right? So the potential is 0. Now at a, x is equal to a, your potential is given v. So see, x is equal to a, you write down a will cut and v is remaining. So potential at a is v. So by that way I have written the expression for the potential, and now you have to put it in the expression, right? That psi n zeroth. Now this is your potential xav and psi n zeroth, and see, if we have to work with, so you know the expression for the wave function, right? So that is, let me take the, I will write it in, now I will write it in terms of the integrals. So before that I will take the a constant outside. X is only the function here, right? So now psi n, you remember this is root 2 by L sin n pi x by L, right? This was the wave function for a particle in a box, right? Here instead of L I should write A, right? Because here the box length is given A. So root 2 by A sin n pi x by A, complex conjugate of that will also be the same because that is a real wave function. Now we are going to get this thing again. So what I will do is that I will remove the root over and put a square there, square of sine, and obviously x is going to be there and dx is there. So I will take v by a square and integral x 2x sine square n pi x by a dx. Now see, 2 sine square n pi x by a, what is that? If I have to write 2 sine square n pi x by a, that can be equal to 1 minus cos 2 n pi x by a. So I need to break it down into two parts, right? X 1 minus cos 2 n pi x by a dx. Okay, and obviously this is 0 to a, right? The integral is from 0 to a, but here you will see that we need to use integration by parts. 0 to a x minus b by a square 0 to a x cos 2n pi x by a, okay, dx. Now from this part, left hand side, you can see we are going to get something by v by a square into obviously x dx. So x square by 2 and it has upper boundary is a and lower boundary 0. And what about this integration by part? Let us do it in this blank page. Maybe we have x cos 2n pi x by a dx. So first we will do the integral for this cos minus a dx or d of dx, that would lead to 1 integral of, obviously, integral of dx by dx. Then we are going to have another integral of cos 2n pi x by a dx. So first cos 2n pi by this would lead to 2n pi x, sorry, 2n pi by a this side, and sine 2n pi x by a, and integration of this side would also lead to 2n pi by a sine 2n pi x by a dx. There is another dx is there, so it is 2n pi by a x sine 2n pi x by a minus 2n pi by a square. Integration of sine will give you plus cos, right? And 2n pi by a, that's why I have written it in a square term. Earlier there was 2n pi by a was there, so this is going to lead to cos 2n pi x a. Okay, now if I have 0 to a upper limit and lower limit, a to 0 upper limit at a and 0 at lower limit, so from the first term we are going to get 2n pi into a by a, so a will cut, sine 2n pi a will cut, and then we have 2n pi by a whole square cos 2n pi. Okay, then minus we will have 0, obviously because x is 0, sine also is going to be 0, so that term is going to be 0. What about the cos part? So this is now minus, right? Minus 2n pi a square cos 0. Cos 0 is 1. So, and what about 2n pi into sine 2n pi? Sine 2n pi means is always 0. So this part is going to be 0. What about cos 2n pi? Cos 2n pi, suppose for, let us see, cos, let us take n is equal to 0. So cos 0. So that part is going to be 1, right? What about uh, what about uh, uh, let us say n equals to 1, then cos 2 pi, cos 2 pi is 1. So cos 0 is 1, cos 2 pi is 1, then obviously cos 4 pi is going to be 1. So this is 2n pi by a whole square, and this part is 0, and this is minus 2n pi by a square, because cos 0 is 0. So overall we are going to get this as, this part is not going to lead to anything, so actually 0. So from here we are going to get zeros, the second integral. So let us see the first integral, b by a square, and this is going to be a square by 2, and this is going to be 0 if I take 0 square, so it is V by 2 is coming my perturbation, the first order, you can say the first order correction, right? So the answer is V by 2. Now the next question, the expression for the nth order correction to the energy of kth non-degenerate, so this is also for non-degenerate level of system EKN, that is the energy of the nth order energy of EKth of the kth system is E, is given by, you need to remember this. This is very easy, this is nothing but this second option, this psi k 0th V psi k n minus 1 integral of this bracket notation. Now we have another question, the seventh, that the particle of mass is confined in a infinite potential. Okay. See, this is directly related to the part what I was discussing earlier. So let me read the question once, that a particle of mass m is confined in a finite potential well with a boundary condition that v of x is equals to 0 when it is when x is between 0 to L and infinity, otherwise that is a normal condition for a particle in a box, so we don't have to think much about that. And this is subject to a perturbing potential. Expression for that potential is given, Vpx is equal to V naught sine 2 pi x by L in the well. Let E1 and E2 be the first and second order correction to the ground state energy respectively. Which of the following is true, is or are true? See, we need to see the first and second order correction to the ground state energy. I have discussed earlier that for second order correction to the ground state, here see the second, here let me highlight maybe once, that for ground state the second order correction is always going to be negative. Why? See, because your ground state means n is always going to be lesser than the m any other state you are going to think, and that's why your energy of En 0th order is always going to be lesser than your Em 0th, and that's why you are in the denominator you have a negative term and in a numerator you have a positive term because of the square. That is why for the ground state the second order correction is always going to be 0. So you have two kind of options here, as you if you see, for A the E2 is less than 0, and for D also your E2 is less than 0. So you have to, and but in one case your E1 the first order correction is 0, and in one case it is also negative. So you have to calculate the first order correction to get to the right answer. So your this your it is given for a first order correction, obviously a sorry in a particle in a box problem, so you know the wave function and your expression for the perturbation is also given, so that is v naught sine 2 pi x by L. So maybe I will take a blank page and I will solve it. So I may need 2 pages here. So we know the psi n, right? Psi n 0th, that is 2 by L sine n pi x by L, obviously, right? And your perturbation is also given, that is V0 sine, I'll just check, I'm not sure, V naught sine 2 pi x by L, sine 2 pi x by L. So your E first order, E 0th first order, right? Because it is and also this is to the first order correction. So psi 0. So sorry, not 0. See, here is a good thing, good example. See, if we are talking about the ground state. Ground state for a, if you remember that first order correction, the quantum number starts from 1 for a particle in a box. It doesn't start from 0. So whatever I have derived till now, or sir has shown you, that is for a general case. So you need to remember for which case what is the ground state. So here the ground state is 1, obviously. So you, instead of sine n pi x, I will write sine pi x by L. So here your let me now write and psi, not psi 0, I have to write E0, not E0 but E1, right? That is my ground state. So that is nothing but this. If I write it in terms of, sorry for this, if I write it now, I have your root over 2 by L sine pi x by L multiply by your V naught sine 2 pi x by L multiply by root over 2 by L sine pi x by L dx, right? And your x, L grows from 0 to L, right? Now let me shorten it down for you. V0 is constant, so I will keep it outside the integral. Now I have sine 2 pi x by L and multiplied by, and also I have 2 by L here, right? 2 V naught by L, that will come outside the integral, and I have sine square pi x by L dx. Okay, so can I make anything out of this? Let me check. If I want to do it, so let me take the 2 inside 0 to L. This is sine 2 pi x by L earlier, and this is now 2 sine square pi x by L dx. So 2 sine square pi x by L can be written as 1 minus cos 2 pi x by L, right? So this is nothing but that your cos 2 theta is cos square theta minus sine square theta, right? And you can write it 1 minus 2 sine square theta, and that's how 2 sine square theta can be written as 1 minus cos 2 theta. That is what I am using, the relationship, trigonometric relationship. V0 by L, 0 to L integration sine 2 pi x by L, and this we are going to get 1 minus cos 2 pi x by L dx. So in one side P0L 0 to L sine 2 pi x by L dx minus V0 by L 1 minus 0 to L sine 2 pi x by L multiply by cos 2 pi x by L, okay, dx. So what I will do here, I can do it in a multiple way. So see, if I take sine 2 pi x by L as P, right, or P equals to sine 2 pi x, like that, and then my dp is going to be obviously I have something in outside that L by 2 pi. Oh, I have made one mistake, I guess, here in the previous question, but that doesn't lead to anything, because but I should don't have the eraser right now, so I should say this is inverse of this, because that's what I have done for a, what I have written is for a differentiation, not for integration. Integration, it is reverse of that, but this doesn't play much, because anyway this is going to be 0, even if suppose it is going to be a square, not this, n pi minus 1, and this going to be minus 2. Anyway, this was going to be 0, right? So that doesn't really affect my answer, but I tried to keep them same. And for now I was also making that mistake. So dp, now for a differentiation case, it is going to be 2 pi by L, sine is going to be cos 2 pi x by L. So L by 2 pi dp is cos 2 pi x by L, okay, and obviously dx this. And I need to write the relationship between L and P also, sorry, x and P. So I had the upper bound, lower boundary 0, upper boundary L. So when x was 0, so when x is 0, my P is going to be sine 0, that is 0. When my L is going to be, when x is going to be L, then my P is going to be sine 2 pi, which is also 0. So you can clearly see I don't have to do the integration. This part doesn't affect. Now this is V0 by L into L by 2 pi, 0 to 0, sine, this part I have taken as P, right? P into cos 2 pi x dx is my dp. If I take so L by 2 pi P dp, right? Cos 2 pi x dx is going to give me L by 2 pi dp. Now anyway, the upper boundary and lower boundary is same, so I don't have to think about the integration. Anyway, the integration was easy, but this is going to lead to 0, right? And what about the second part? My hinge says that it is also going to be 0, because it is a sine function and we are doing it for so long, right? V0 by L, 0 to L, sine 2 pi x by L dx. Integral of this going to lead to your L by 2 pi. Obviously integral of a sine is going to lead you to a minus 1, and then cos 2 pi x by L, upper limit is L, lower limit is 0. So this part is V0 by 2 pi minus cos 2 pi minus minus plus V0 by 2 pi cos 0. Cos 2 pi is 1, cos 0 is 1. What I was saying, this is 1, cos 0 is 1. Okay, So this is v0 by 2 pi plus v0 by 2 pi. This is also 0. So as you can see, your first order correction to the ground state is 0. So your option A is correct, where your first order correction is 0 and second order correction is negative. By that way you can solve the problem, but as we are almost we are at 9:10, so I think I have to stop the session. But what is there, what I had in mind was that we are going to solve some more numerical problems which I had uh, collected from different books like J.T. Lee or Macquarie Simons, even from Atkins. So like a problem in a particle in a box, where a similar problem like the previous one where the perturbation is given. Now another problem similar, the perturbation is given, but now your wall length is different. So this kind, and this is another kind of problem I found, some matrix kind of problem where your Hamiltonian is given in a matrix format, so you need to get the eigenvalues and eigenstate of the unperturbed Hamiltonian. So this kind of problem I thought we would have the time to solve, but anyway I am sharing the questions with you in the drive folder, Google Drive, and obviously you can pause the video and see the question and try to solve it by yourself. Anyway, in the next class we will come back and solve these numerical problems, so that way your concept related to the perturbation is already build up, and you, as you will solve some numerical problems, we will solve together. So that will that will, by that way we would be very we will be confident about these numerical problems. Whatever comes in the question we will be able to solve. So please try to look at the questions beforehand, before joining the class in the next session, the next Monday, sorry, the next Tuesday, that is I guess 8th October. On that day we will try to solve these numerical problems. Anyway I share the notes with you, and try to solve it by yourself, and then we will solve it together. So with that, today we are going to stop here. I hope the session was useful to you, and if you had any doubt you can post it on the discussion forum or in the comment section. I will try to answer them, and maybe on the next session itself if I see any questions. So with that we are stopping it today. I hope the session was useful to you. I hope to meet you on the next session. Thank you.